Yes. So we just cut it and remodel just a cross section. Yes. And this type of problem is called plane strain modeling. Yeah? So if you remember, in 1 week, I can't remember which week, we solved problems of soil foundation. Yeah. So so you have step-by-step solutions. Yes, I strongly suggest you review them as well, because that's why every week we were solving problems. So that problem, it was a plane strain problem, because when we model soil, so it's a very large body, we model just a cross section of a large body, yes, and this is where we used plane strain element. So, do you want to model this one? Okay, let's model. Okay, so plane strain. So we'll model 3. So what the way? How would you model it? So you need to develop this model. So this is a problem, or one of the problems. Probably its weight will be 25%. So because it's quite simple. So you can see just plates around, and you just need to fix to it. So how would you model it, just from modeling point of view? Quick way. So it can be done in 5 minutes, maybe even 3 minutes. Yes, and it can be done in 20 minutes. So what's the quick way of doing it? Yeah, exactly. So we model square, we mesh it in such a way that we have elements of 0.25, okay, and we just select these internal elements and delete it. So work can be done in 3 minutes. Okay? So if you want, we can solve it quickly. So we'll start next second. So data is given. So we'll change the parameters, because I don't think it is steel. It's most likely concrete. 50 millimeters cannot be steel. And steel culverts are usually made from profile steel, which is quite thin. So okay, let's assume it's concrete. So it's a concrete with a thickness 250 millimeters. Okay, so let's use Newton. Let's go use standard SI units. Okay, so you can see that we can model. First of all, we can model a square mesh 3 by 3 meters, and to have thickness 0.25 millimeters. Yes, what we can do. We can actually create the initial mesh with 0.25 by 0.25 elements. Yeah, so initially we'll create a 3-meter beam, yeah, subdivided into elements of 0.25 meter length. Then we extrude them to complete a square, and then remove the internal part. Okay, let's create a 3-meter beam first. So insert node. So we need to start with one node. Okay, so I'm going to insert this node into a beam. So it's in meters, yes. So we go to tools, extrude. Not insert, extrude. Extrude by 3 meters in the X direction. So that will be the base of this model. Yeah? So we know that we need elements of 0.25. So we'll just go to mesh, subdivide. Okay, so how many subdivisions? Let's not use our brain, let's use computer brain. So we need 3 divided by 0.25.
X direction, not 3 meter.
Yeah. So it tells us 12 elements, 12 subdivisions. So in this way, we will subdivide this beam into 12 elements of 0.25.
What is it? 3 divided by 2.5.
2.25.
So next step, to create a plate, extrude this beam into a plate. Yes? And again, the plate is 3 meters tall or high. Yeah, so we will extrude it again to the step 0.25 to create a square. So extrude it in the right direction. Yes. And again, 3 meters by 0.25. Okay, yeah. So increment is 0.25. Point
Y
increment is
direction
0.25,
0.25
but repeat 12 times.
repeat 12 चोटि गर न पछि डिभाइड
3
गरेर
divided
गर्न
by point. Now, we don't need the beam elements in the model, so we can select source, delete. We need only the beams.
प्लेट डिलिट गर्नु पर्यो हैन
We need to select all beams, so select them either just dragging mouse around it or just click this button. Select all.
यसो थिच्दा नि मिल्दैन त नि
Selecting all beams. Yes, click this line. So each of these square elements is 0.25 and 0.25. Yeah, so if you look at the problem, so that will be the thickness of the wall. So what we can do, we can remember there is a function here called select by 3D region. So hope you use it when you develop your bridge models. So this allows us to select the inner core, the inner elements. I just click the nodes, diagonal nodes, this node and this node, so diagonal nodes. And it selects the element that we want to delete. Yes, click OK, select. And that's it. Hit delete button. So use select by 3D region.
property सेलेक्ट गरेको
And then select the diagonal. These the diagonal points of the area that you want to select. Just 2 points. No, 2 points. Okay. And click OK. And it selects and click delete. Now, if you leave it like this, it's not a good model. I mean, it's good starting finite element, but it's not a good finite element model because it has only one, you see? So we expect stresses, deformations in the walls and elements of this structure, of this color. Yes. But what we have done now, you see, we have just a single element through the thickness of the walls. So this element will not be able to predict how stress is distributed across the cross section. Yes? So we need at least 4 or 5 elements across the thickness of structure, yes, to properly capture stresses within the thickness. This, yeah? Because one element will not give us a good result. Okay? So what this means, we need to subdivide all these elements, mesh subdivide. So make sure that we select plate, so select plate, select them all. Yes, and let's say, and you can see this like a line, A and B lines. It's a direction and B direction. It means how many subdivisions in the A direction and how many subdivisions in the B direction. So, okay, let's do it 4. Okay, let's say A4 and B4. Okay, click apply. Okay, so now it looks much better. You can see we have at least 4 elements across the thickness. So if we model bending deformations of these walls, so we should be able to see bending distribution, and we have points on the middle as well. So this model will give us much better results. So that's all for the model, for the mesh. No, it's not the model, I mean for the mesh. Yeah, so that's our mesh. Now we need to complete the standard steps. Apply boundary conditions, loading, and material properties. Yes? So to complete the model. So far we have the mesh, yes, but we don't have the model. So we need to complete the model. So what we have?
अनि रोटेसन पनि एक्स्ट्रा रोटेसन चाहिँ
So it shows that you can see it actually supported only at these 2 points. Yes. So and these 2 supports the so-called pin supports. So they're not rollers, they're pin supports. So it means the bottom corner nodes, yes, needs to be support. Again, before we start applying the restraint conditions, we need to turn this model into 2-dimensional model. So don't forget, yeah, if you model 2-dimensional structures, yes, we need to turn, because at the moment it's a 3-dimensional structure. So we need to use cases freedom, yes, and look for preset conditions. You see, 2D plane stress or 2D plane strain. So basically 2D plane structures. What we model now, we model a 2D plane structure. So this structure will have only X and Y degrees of translational degrees of freedom. So 2D plane. So now if we go back here, and if we go to what we want to apply restraints on the nodes, yeah? So we go to attribute node restraint. So all the X and Y degrees of freedom active, yeah. So other one we can just disregard. Now, according to the problem, these corner nodes are restrained in X and Y direction. Yeah, as pin connection. So we just say select X and Y and select these 2 nodes. So we select these 2 nodes. Yes, and we apply pin conditions. At this node.
छैन होला त्यसो गरेर चाहिँ आउँछ पहिला
So what else?
के भयो त
Material loading.
होइन यहाँबाट यति छ यतिमा आउँछ कहिलेको
Loading.
Apply गर्नुभयो?
We'll see.
লাগানো মানে তারপরে
হ্যাঁ দুইটা নোট সিলেক্ট করে apply করা যাবে।
Now you can see that the load acting on the top,
পিন বয় মানে
yes, on top of the structure is 7 kilonewton per meter, seven kilopascal.
Roll by y generally y1.
Now again, but we model two-dimensional structure. Two-dimensional structure. So how we can apply pressure to a two-dimensional structure? I think we did it some time ago. If we go to plates, yes, there should be a load called edge loads. So these are actually pressures that apply to the edges of plate element. You see, there are three types of load can be applied to a plate. Point load, so these are loads applied at the nodes. Then face load, so it's loads applied at the perpendicular at some angle to the face, like a so-called transverse load. Okay. And then edge load, it's loads applied to the edges of the beams, of the plates. Okay. So what we have in our case, we have a series of plates, yes, and we have load acting on the edge. Okay. So it's not a normal load. Yes, it's not transverse. It's a shear stress. Yeah? I think it's transverse shear. The transverse it will be perpendicular or edge. So just hold on, I'll check. Because they show edge normal. So normal it means again normal to the edge, not normal to the element. See, you can check. You can check each load by, see, it actually shows you an icon how the load is applied. Okay, so we're putting edge, and normal pressure, it's a normal to the edge. Yes, not normal to the plate element, it's a normal to the edge. So if we select normal to the edge, that will be the load that what we need. Yes? We need to apply this edge normal pressure is in 7 kilopascals, 7,000, yes, so it's 7,000, and acting in the downward direction. So whether it's plus or minus, I mean, we don't know. So because again, it depends on the how element is created. So we can try both. If negative is not right, you just change to positive. Okay. So now how to apply edge pressure? You actually need to apply to the edges of the elements. You see, I'm going to just zoom in. And edge pressure, it means you actually click on the edge. Just click. I think you should be able to, I'll try, if you just use your mouse and just drag it around the edges.
You can use that.
Let's do it manually. You just need to click from inside. You see what I'm doing? Clicking from inside, but very close to the edge, to select the edge. Because otherwise it will select whole element or other element. You see, just from inside of the element and coming close to the edge and select. Just clicking inside. Oh, so you need to be careful. Clicking.
You can use the 3D select.
Yeah, I think so. Yeah, you should be able to. Yeah. You should be able to select it. Let's try 3D select.
Yep.
From here, here. Yeah, you see it's selected, yeah. So you just use 3D select, and then just click
পরে সিলেক্ট করবো
click first node and last node. Yes, and click, now, let's see if the direction is correct. Click apply, yes. See, we selected negative, so it points in the right direction.
Driver day,
So what's new, and like you haven't done it before, so what's new we just done? So to apply pressure to a plate, yes, like this, like a two-dimensional plate, yes, you have to use H pressure. H pressure. And then specify the value of pressure, yes, and give the right direction. Okay, so we applied pressure. Okay, now let's create properties. So we go to global properties. So we should have, so we don't need beams, because beam property was created automatically. You can keep it in the model, right? We can delete everything. I don't need, so I can delete it. So it's for beam property. But for the plate property, yes, we need to fill it, fill the data. So let's assume it's concrete, because I don't think 250 wall could be solid steel. Yeah, so let's use import material property. Let's maybe it's steel. Let's use, let's say, concrete. So what concrete we use? Like AS3600. Yes. What concrete strength do you like? Any. It doesn't. At this stage, it doesn't matter. So let's use 50 MPa. It only has effect slightly changes the modulus of elasticity. The strength of concrete. Now for the thickness, I mean that's what's important. The thickness. Remember what we are modeling. We are modeling a culvert. Yeah? Right. So what is the thickness of this element that we model? No. I mean, again, we use plane strain element. So plane strain element is just a cross section. So plane strain elements have thickness 1. Just unit thickness. Okay? Yeah, we need to, you're right, we need to change. So let's change, so thickness 1. Okay. And what we haven't done, we should have done it from the beginning. Yeah, we need to change the type of element. Because the default one is 3-dimensional plate, yeah, but we modeled 2D plane strain. You see? So it still has thickness. Yeah? And that's what we specified, thickness 1. So there is no thickness, just look at the problem. There is no thickness. So what thickness to use? So we use, if it's a plane strain model, so we use thickness 1.
꽃을 다 본, plane stress 본대로.
So plane strain, material, it's linear, thickness 1. So I think that's all. So this should be step 1, change the plate type to 2D plane strain, then specify step 2, specify material properties, step 3, specify thickness 1. So that's all.
다
Now we can
Stress
try.
strain
So this is a static analysis. Yes, linear static analysis. We're going to introduce non-linear
ChatGPT 다
properties
보죠.
of concrete.
Sorry.
We can see whether concrete is likely to fail. Yes, just from the stresses. Okay, just,
이렇게 그리고 있어요.
이노가 이렇게 다 하나니.
calm design for the culvert to determine von Mises stresses. Because it's steel. Yeah? If it's concrete, we can look at principal stresses, maximum principal stresses. So remember, von Mises stress, it's a damage criteria, which is used for materials that exhibit ductility, such as steels, aluminium, metals. Yeah? Concrete is not ductile material. Yes, it does not yield. Yeah, so we cannot use von Mises stress. We can use principal stress, for example. One of the sigma 1, sigma 2, sigma 3, but we see one of just to find maximum. So we open the result. Yeah, let's change scale first, see whether it moves. Let's move. Doing the right deformation at least. Yes. So let's first look at the contours of displacements, just to understand how much or what the maximum displacements in this color. So we select, let's say, contours, displacements, global. If you want to see total displacements, not along the x and y, because you can see the elements will be displacing in both x and y direction. Yes. If you want to see the total displacement, yes, we can select not dx, dy, dz. We can select dxy. So dxy is a total displacement in the xy plane. So the program will automatically calculate the maximum displacement. We can see it's quite small displacement. Expected small. So you can see the displacements are very small. Probably the structure can be optimized. So you see displacement is so small. Now displacement. No, we'll check the stresses first. But if they're also small. So obviously structure can be optimized. We don't need 250 walls of concrete. Maybe 100 millimeters of concrete will be enough. Oh, that's actually, I invented a new design problem for this. Find the optimum thickness of the culvert. Now let's change the stresses. So what stresses we want? We want principal stresses. So it will be that they combine. So we don't know which one. So let's look at the principal sigma 1. Okay, so what we have? 300. So we can see here, so this horizontal part of the culvert will, you see, positive stresses, it means tension, negative means compression. So the bottom stresses will be in pascals 335 kilopascals. So it's not even megapascal. So the stresses are really small. So the culvert can be optimized. So these are principal stress sigma 1, sigma 2. Yeah. So sigma 2, remember, it's a maximum negative stress, and sigma 1, it's maximum usually positive stress. So in terms of principal compressive stresses, they're also quite small. So this structure, again, for this particular loading conditions and boundary conditions, yeah, the structure is clearly over designed. Yeah? So what we can do, we can optimize it. Yes, let's just close the results. Let's remove couple more areas. Yeah? Let's make it thinner. So the problem is find the optimum thickness of the culvert. Okay, let's remove, let's say, two rows of the evidence. Let's remove more evidence. So we can make sure that plate select is on. Okay, select, use 3D region select. Yeah. And let's select 1 and 2 from here. And so 2 rows. And we select two rows or 2 lines of finite elements. So instead of 250 millimeters thickness, this culvert will become 125 millimeters. Okay? So we can click OK. Yes, and click delete. Okay? So you see we have another model.
क्यों आ रहा है फिर ऑर्डर जाओ
थिकनेस निकालना
Now we can rerun it.
खै अब त्यही हो होला नि त कतिसम्म स्ट्रेस पास गर्छ नि त्यसमा
We rerun it. And go to results. Okay. What we get? It's a principal too, so let's check the deflection first. Displacements, global, DXY. Still quite small, 0.5 millimeters. So we don't structure, we want structure to be rigid. So the deflections are alright. Now if you check contours of stresses, cut line, principal, stress. Okay. So it shows that we have 1.5 megapascal tension. That's perfect. For concrete, it's, you know that tensile strength of concrete is just couple of megapascals. Yeah, 2-3 megapascal. So actually from design point of view, if we want to avoid cracks in concrete, yeah, so we need to keep maximum tensile stress under like 2-3 megapascal. Yeah, so what we have here, so the maximum tensile stress is 1.5 megapascal. So the concrete will not crack. Yes, and, so we can say
इकोनोमिकल डिजाइन
optimum thickness for this culvert is half of 125 millimeter. So you see another practical problem, another practical design problem. Yeah? So we're using finite element modeling. Yes, we can find the best parameters for the structures that we design or we need to use. So, okay. So how we go to start? Any questions?
खै त्यो यस्तो गोल कसरी गर्ने हजुर
No, we'll look at this maximum stress.
बेलामा मोबाइल प्लेन स्ट्रेस
Maximum stress.
त्यो हेरेर पनि बुझेन नि फेरि
But again, now you need to use your civil engineering. Right? Did you study concrete? Okay, so what's concrete stress? Tension. So again, there is a very good rule of thumb. It's roughly about 1/10 of the compressive strength. Roughly.
Should be fine.
So, I mean, if you use 50